Okay, on this video, we are going to introduce the concept of rotational kinetic energy. Now, at this point, what we've done in class, we have linear kinetic energy when an object is just moving in a straight line. And now, hopefully we understand enough that once an object starts rotating, its moment of inertia is going to affect how fast it's going to move based on and its radius and its mass and so on. Okay, so let's look at a couple of equations before we get started with this. Okay, if I've got an object that's sitting on top of a ramp, it's going to have, at rest, it's going to have gravitational potential. So we have UG equals mgh. Okay, so that's an old equation of ours. All right, if this object were to just slide, so let's say there's no friction, it's not going to roll. So it's just going to slide down the ramp. Okay, it doesn't matter what shape it is. Okay, and at the bottom of the ramp, when all of this gravitational potential energy is going to be transferred into linear kinetic, so we are going to have kinetic energy. Now, this sometimes will be called translational, okay? And remember, translational or energy on the tangent of the circle. Okay, so we've dealt with that term a little bit. Translational energy means the same thing for us. So 1/2 mv squared, okay? So if I didn't have any friction on this, we know that the gravitational potential here is going to be equal to the kinetic at the bottom. So I can write an equation, put these together, and I can say mgh equals 1/2 mv squared. Okay, and I can calculate the velocity at the bottom or the height, depending on. So if I was solving for b, this would be square root of 2gh. Okay, once again, that's pretty common work energy theorem type of equation when we're dealing with concepts on an incline or above the ground. Okay, now that this object's going to roll, once it begins rolling, it's not going to go as fast as what it's going to go if it slides without friction. Okay, so now we're going to have, in addition, we're going to have a rotational kinetic energy. And in our study of rotation, hopefully we can just kind of fill in this equation by now. Okay, so 1/2 mass and a straight line is the object's inertia. Okay, so even though it's rolling down a ramp, it still has straight line energy. So now we're going to replace the mass with the object's moment of inertia. Okay, and instead of the tangential velocity or the linear velocity, now we're going to substitute omega for the radians per second that is rolling through. Okay, so now in our work energy equations or in our conservation of energy equations, we have three things to think about. Okay, whenever an object is rolling, it has both kinetic, translational, and kinetic energy rotational. Okay, as it's moving in a straight line and rolling. Okay, now if something's just spinning in place, there is no linear kinetic energy. It's all in rotation. Okay, so if I have a wheel and put an axis right in the center of it and make it start just rolling around, okay? So in that scenario, we wouldn't have any translational kinetic energy, okay? So let's now jump to this, and I'm gonna leave this up here on the board because we're gonna come back to this at the very end of the video, okay? I'm gonna show you a way to get to this equation and derive it out. It's a little bit complex. Luckily, it's the same process every single time. So if you just kind of memorize the process, then you'll be pretty good at deriving the equation out for the remainder of the object. But we're just going to use it for this solid disk, okay? So a solid disk is sitting at a ramp of height h, okay? And we have a 2.5 kilogram disk, and the radius of the disk is 0.15 meters. And we're going to roll it down the ramp. And at the bottom of the ramp, it's moving at 3.5 meters per second. Okay, so I actually gave you an extra piece of data here, and we could use this and put it all together, but we'll save that for later when we get to that point. Okay, well, let's solve for the translational kinetic energy. So 1/2 mv squared. Okay, so we're gonna have 0.5 times our mass, which is 2.5 kilograms, times our linear velocity. And that's going to give me 15.3 joules. Okay, so there's the linear energy. Now, the rotational energy, and of course, once we throw in the moment of inertia, this always gets to be a little bit more complex. But we need this number here, okay? So omega is V over R. Like I said, I'll show you how to sub in all of this stuff here in just a little bit. Omega is V over R. So let's go ahead and get that calculated. So we have 3.5 meters per second divided by 0.15 meters. Okay, that's going to give me our rotational velocity of 23.3 radians per second. All right, it's starting to get pretty long already. So let's go ahead and solve for rotational kinetic energy. So 1/2 I omega squared. So we have 1/2 now. The moment of inertia for a solid disk. 1/2 Elm R squared times omega squared. So we're going to have 0.5 times 0.5, which is 0.25. Okay, times the mass. So I'm going to go ahead and just say 0.25 times the mass of the object again, 2.5 kilograms, times our radius, and then times omega, so 23.3. Oh, like I said, you can see how long these types of problems are going to get. And that's going to give me a rotational energy of 7.63 joules. Okay, so here's where we look at this problem now. At the bottom of the ramp, the total energy of this system is these two added together. Okay, because all of the object's gravitational potential at the top, so instead of saying mgh equals 1/2 mv squared, now we have to say mgh equals 1/2 mv squared plus 1/2 I omega squared. Okay, so if we add these two numbers up, our total energy is 22.9 joules. Okay, so let's go ahead and say this is 22.9 joules. That's the total energy of our system. Okay, so if I'm wanting to solve for height, now I'm going to say that energy equals mgh. Okay, so all of my kinetic energy at the bottom of the ramp is now going to be equal to gravitational potential energy at the top. Okay, so now I can solve for height. So we'll say E over mg. Okay, so I'm going to take my 22.9 joules, and I'm going to divide that by mg, and my mass is 2.5 kilograms times 9.8. And that's going to give me 0.936 meters. Okay, so this is a 93.6 centimeter high ramp to get this velocity at the bottom of it. Okay, now let's change gears here. This is a lot of work, and I don't like to do this much work. I would rather know how to simplify this expression and get to a single equation. Okay, so let's try to write all of this in this format. Okay, because sometimes it's helpful just to know if I put several different objects on an incline, release them all down, which one's going to win. And it's going to be different for an object sliding. So if we have an object sliding with no friction, this is the final velocity is going to be equal to square root of 2gh. If I take a hollow ring and I roll it down a ramp, and I have a different moment of inertia than I will for this disk. Or if I take a solid sphere versus a hollow sphere, those are all going to reach the bottom of the ramp at different rates. Okay, so we need to understand which one's going to be able to get there quickest. So let's erase this real quick. And let's look at this all together into one problem, okay? And what did we say the height was? 0.936, we're gonna go ahead and use that. Height equals 0.936. And let's solve for this final velocity real quick, okay? So, conservation of energy. So the gravitational potential at the top of the ramp is equal to the sum of the rotational and linear kinetic energies. Okay? Now, I'm going to do a two-part substitution here. Okay, so let's go. mgh equals 1/2 mv squared plus 1/2 mr squared for the moment of inertia. And then remember, omega is v over r. Okay, so if I sub in v over r in for this and then square it, v squared over r squared. All right, now this is what's interesting. It doesn't matter if I put an object on an incline that has a mass of 10 kilograms or a mass of 20 kilograms. We should know by now the mass is going to cancel out of the equation. Okay? It also doesn't matter, and this is the tricky part. You would think that an object with a larger radius measurement will finish at a different time down the ramp than one that has a smaller radius.
Hale, please come to the front office.
R squared divided by R squared. Front office, please. These cancel. So notice our equation becomes very simplified. We have GH equals 1/2 V squared plus 1/2 times 1/2 is 1/4 or 0.25. So 1/4 V squared. Okay. Now this is starting to get a little bit more simple. Okay. If we add these two together, this is 2/4 plus 1/4. So G times H equals 3/4 V squared. Now, let's write our equation and solve for H, or solve for V, I'm sorry. If I rearrange this, I'm going to have V equals the square root of 4/3 GH. So notice how this equation simplified and gave me the velocity at the bottom of the ramp for a rotating disk. This would be the equation for an object sliding with no friction down that same incline. This object's going to get there first. This is times 2. This is only times 4/3, okay? Every single object is going to be some ratio. The object that slides is always going to get there first, assuming there's no friction, versus any object that's going to roll, because some of that linear kinetic energy has to go to rotation. Okay, so it's going to lose some of that linear kinetic energy. It's not going to be moving as fast. Okay, so let's solve for this. Square root of 4/3 times 9.8 times our height was 0.936 meters. Okay, so if we square root that, we are going to get approximately 3.5 meters per second. Okay, so once again, that's how we get back to that number. So know this process. It will definitely pay dividends in the long run. One thing is nice. The only thing that's ever different about it is instead of 1/2 mr squared, it's going to be some other fraction. Okay, so it depends on whether you have a solid disk, a hollow disk, okay, a solid sphere or a hollow sphere. Those are usually the 4 primary ones that are done. Okay, so you just have to know what this number is in front. Okay, and it'll make all of this very simple. So the process is the same every time.